Chemical reactions in aqueous solutions, Part 1. There are three types of chemical reactions in aqueous solutions, including precipitation, acid-base, and oxidation-reduction, also known as redox. What a precipitation reaction is when two aqueous solutions react to create a solid, and that solid is called a precipitate. In blue, there are two aqueous solutions, iron nitrate and sodium hydroxide. In yellow, there is a sample precipitation reaction for these two reactants. The product side has iron hydroxide and sodium nitrate. Iron hydroxide is a solid and is a precipitate in this reaction. Another way to look at this is with an ionic equation. In green is the ionic equation for this reaction. Ionic equations break the soluble or aqueous solutions into ions. Each ion is shown with a charge and an AQ in parentheses to represent that it is aqueous. For example, iron is represented by Fe for iron, +2 for its charge, and AQ to show that it is aqueous. Solids such as iron hydroxide aren't broken into ions and remain the same. Looking at the equation, you may have noticed there are ions that are the same on both the reactant and product sides of the equation. These are called spectator ions and can be ignored, so we'll cross these out. The spectator ions in this case are the NO3-, the nitrate ion, and the Na+, the sodium ion. Next, we'll rewrite the equation without the spectator ion. So you're left with the iron ion plus the hydroxide ion, and the product would be iron hydroxide. And so the only product left is the precipitate. And the general purpose of a net ionic equation is to just focus on the principal substances and ions in an equation. One last important part of precipitation reactions is solubility rules. These can be used to predict whether a precipitate will form. Here are some of the basic solubility rules that if you would like to look at further, you can pause the video for. When using the solubility rules to predict whether a precipitate will form, if the salt in the reaction is soluble, no precipitate will form, and if an insoluble ionic compound is part of the reaction, a precipitate does form. The next reaction in an aqueous solution is acid-base or neutralization, and the reactants for this are acid and base, and the products are water and salt, which is an ionic compound. One example of a neutralization reaction is hydrochloric acid, an acid, plus sodium hydroxide, a base, that results in water and sodium chloride, which is a type of salt. And the net ionic equation for this reaction and all neutralization reactions is a hydrogen ion plus a hydroxide ion, which results in water. Titrations go along with neutralization reactions, and it's basically the measurement of neutralization process, and its purpose is to determine the unknown concentration of an acid or base, and the endpoint is basically the point of neutrality, so when the moles of hydrogen and hydroxide ions are equal. This is a visual of titration, and it can be done with either the base or the acid being unknown. Either way, the known concentration goes in the burette, and the unknown concentration goes in the Erlenmeyer flask along with an indicator, and the known concentration is slowly released into the unknown concentration until a color forms and indicating neutralization. This goes back to the original neutralization reaction, and with the titration you're going to find that 100 milliliters of base is required to neutralize 20 milliliters of 5-molarity hydrochloric acid. So you're going to want to find the molarity of the sodium hydroxide, and you're going to need an equation to do this. This equation is written in green, and it is the molarity of an acid times the volume of an acid is equal to the molarity of a base times the volume of a base. And then you're going to substitute in everything you know from the titration to find the unknown. Substituting in the known values, you're going to get the equation 5 molarity times 20 milliliters equals the molarity of the base times 100 milliliters, so 5 times 20 equals 100, divided by 100 equals 1, so the molarity of the base with sig figs is 1.0 molarity sodium hydroxide.
Created using Powtoon.